Hello everyone. Let me start with a simple question. Have you ever noticed what happens when a moving bus stops suddenly? The passengers inside are thrown forward. And when the bus starts suddenly, people feel a backward jerk. Why does this happen? These everyday experiences point us to one of the most fundamental principles in physics, Newton's first law of motion. But before Newton, Galileo had already challenged Aristotle's old idea that motion requires continuous force. Newton took Galileo's work and shaped it into a universal law that changed the way we understand the universe. Newton's first law is also called the law of inertia. It states every body continues to be in its state of rest or of uniform motion in a straight line unless compelled to change that state by some external force. In simpler words, times a body at rest stays at rest unless a force acts. Times a body moving with constant velocity in a straight line keeps moving in that state unless a force changes it. This law is revolutionary because it tells us that force is not required to maintain motion. Instead, force is required to change motion. Now, let's understand it logically. Newton said that both rest and uniform motion are natural states of a body when the net external force is zero. Think about a book lying on a table, it will remain there unless pushed. Similarly, a satellite in deep space continues moving at constant velocity even when no engines are firing. Mathematically, Newton's law connects with the relation F equals m into a. If net external force F equals 0, then acceleration A equals 0. That means velocity does not change. Examples of inertia are all around us. Times when a car stops suddenly, passengers lurch forward because their bodies resist the sudden change of motion. Times dust flies off a carpet when shaken because the dust particles resist the change in rest. Times a coin placed on a card falls straight into a glass when the card is flicked away. For centuries, people believed that a force is needed to keep things moving. But Newton's law shows this is wrong. Continuous force is not needed to maintain motion. Motion continues on its own unless opposed by forces like friction or air drag. So in real life, we feel motion dies out because resistive forces are always present. But in the absence of resistance, uniform motion goes on forever. Let's solve an application problem. Imagine a spaceship in deep interstellar space. Its engines are turned off, and there are no nearby planets or stars exerting gravity. Step 1. Net external force F equals 0. Step 2. Acceleration A equals F divided by m, which equals 0. Step 3. With no acceleration, the spaceship continues with its existing velocity in a straight line. So the answer is, the spaceship keeps moving forever with uniform velocity. This is a perfect example of Newton's first law in action. Let's quickly recap. Newton's first law states that a body remains in its state of rest or uniform motion unless acted upon by an external force. Rest and motion are both natural states when net force is 0. Inertia is the tendency of a body to resist changes in its motion. So to sum up, force changes motion, it does not sustain motion. This law doesn't just explain why passengers jerk in a bus or why dust flies from a carpet, it explains the motion of planets, rockets, and even satellites traveling through space. I hope you now have a clearer understanding of the law of inertia. See you in the next session, where we'll explore Newton's second law of motion, the real mathematical backbone of force and acceleration.